Good afternoon, guys. Hello, those who are here. After 5 saying good evening is also accurate, right? Um, Anyhow, I'm glad you are here. Let me share screen. Recording started. Sharing the entire screen. Now you can see my screen. All right. So let's see. We have quite a few people. Looks like few of them are still joining. Let's give them another minute. Time-wise would be fine today. Someone reconnecting. All right, guys. So how have you been? You enjoyed one lab week off, and as you know, tomorrow you have no lab either. However, you will have lab on 11th, and as I wrote in the announcement, 10th is religious, no, not religious, it's Columbus Day. So that's why I'm giving a lecture today, but next Monday we are not going to be meeting. All right. Who else is joining? Very Corey joined. All right, guys, so good afternoon again. So today's discussion is actually pretty much covered. As you know, this was a 2-week rotation. I covered the theory of two labs. And next Monday you will have no lab, correct, MD? MD Bhaiya, you are right. You don't have a lecture. Today's lecture is going to be for next week because tomorrow you do not have a lab. The schedule says no class tomorrow. We don't have a lecture next Monday because we are giving that lecture today. Next Monday is a national holiday. Okay, next Monday is a national holiday, so we are clearly it's totally closed. So that's why I'm giving it today. So basically, you will also have opportunity to review the class next Monday, those who wish to. So you have no lab tomorrow. Your next lab is on October 11th. That's what I am looking at the schedule in the academic calendar. I think I am correct on that. All right. So yes, good. So as you know, you have many of you are one half of the class did steam distillation, other half did succinate extraction, and I discussed the theory of both. And next week you are only going to swap them. So those who did steam distillation will be doing succinate. Those who did succinate last time, you will be doing steam distillation. Now that here you have people from both groups. No, I think last week it depends on which room you are, Anastasia. In one room did succinate, another room did steam distillation. So if you did steam distillation, you will be doing succinate. If you did succinate, now you will be doing steam distillation. Anastasia, it is just the other one. You heard both did succinate? Well, I did not hear that. If that is the case, then that is the case. So maybe my understanding was we did not have enough succinate apparatus, and that's why this is how we used to conduct. It is quite possible that they have enough, or they had enough succinate such that everyone did the same thing. That's a possibility, which if it happened, that's good. Nothing wrong with that. Those who did in 11 or 9, did you did succinate as well? Anyone here from 1109? Yeah. So Amira, which one you did in 1109? Which experiment you did? You also did succeed. So that means Anastasia was 100% right. Both group did succeed, meaning this time next week you will be all doing steam distillation. Steam distillation apparatus is relatively less difficult because it's just the distillation setup. Yeah, you did with Walker. Yeah, Walker is not a professor. They're all graduate students. They're PhD students. So you can just call them Walker. They don't have. They're TA. They're just TA. So you can just call them by name. You don't need to say professor. They're not professors. None of the TAs are professors, but they are PhD student. Anyhow, so so in any case, so have you? Uh, so you have the theory for steam distillation. I have shown the calculations in the last class, and we will be using the same to do some practices because such calculation will also be in the exam. Now, as per the syllabus, we are going to have a what is it called? Let's see if I have the syllabus here now. A midterm on 25th, I believe. And on that day you will be doing analyzing using IR, NMR, and GC+MS. Analysis of the products that you are collecting or saving, because both substrate extraction product, you are going to save them. Equally, you will save the product you get from steam distillation. And following week on 18, you will be doing a synthesis of the same cinnamaldehyde from a different thing. I'll discuss about that on 17. And then following week, so you can see it's almost like a 4-week lab, not almost, totally 4-week lab. Following, we'll analyze those products. So analysis may become a shorter lab. But in any case, there is not going to be any more theory, and that is the reason that day I'll give you the midterm. Midterm is going to be in person. I sent you the announcement. It's to my knowledge that 12:30 is a good time for all of you because that was the originally lecture time. That way we can do on the day in person. I'll announce the room later. So that means if I cover this GC+MS, then you have all the theoretical knowledge of all of them. Here you have learned in Organic 1, NMR we did, and now I'll talk about GC+MS. Now, GC+MS is, those who have done GC, you know, GC stands for gas chromatography. Gas chromatography you did on Organic Lab 1. Those who did with me, I discussed that. And all the mechanism and theory was discussed there. In the end, you get a gas chromatogram. Chromatography is the method, technique, and the picture you get almost like a spectrum, except it's not really a spectrum. It is called a chromatogram because it's not light absorption thing. It is about the retention time. So that's why it is called chromatogram. So a chromatogram looks like different spikes of various area and coming at different times. So information you are getting is the times and the corresponding area. So that time is called retention time. And retention time definition you should know already. It is the time a sample stays inside the gas chromatography machine, from the moment it enters the column until the moment it exits the column when it detects. So that is the length of time is called retention time. As you understand, how long it retains in the column, that is retention time. Starting from the point the sample is injected until the time when it exits. So that means the length of time it stays inside the column, right? So you get retention time for different compounds, and each retention time corresponds to a particular compound, right? That's why you learn in your experiment you had two different compounds, you got two spikes or two peaks, and you analyze them for their concentration, measuring their area of the peak. That was inorganic one. Now, you have also heard at that time, those who were in any lecture, in fact, there are how the detector detects. There are four types of detectors. The most common and cheap and yet versatile is thermal conductivity detector, TCD for short. It is most popular, common, and also cheap. So goal is it detects the time a sample comes in and creates a spike. There are other detectors. Second one is called flame ionization detector. It is more sensitive, but it is slightly cumbersome because it requires an additional gas, and that has to be connected, has to be uh, ignited, and that uh, it causes ionization of the sample and produces a signal from the electric current it produces. That is less common. However, many research labs do have because of its greater sensitivity. You don't have that. And it actually people try to avoid because of this additional gas requirement. Now, the most sophisticated, most accurate detector is a mass spectrometer itself. What is mass spectrometer? What is mass spectroscopy or spectrometry? That is something that is also discussed in lecture. Those who have done organic uh, 1 and 2, you have seen mass spectrometry was part of one of the chapters. So I will go over that briefly and indicate when these two things are combined, gas chromatography with mass spectrometry together, it becomes a monster. Very, very powerful, effective monster. Why? Because gas chromatogram separates compounds into individual components. For example, here you get a gas chromatogram, three compounds produces three peaks. Now, if the detector is a mass spectrometer, then as soon as the compound exits the column, that exited from the exit port, it enters into the into the mass spectrometer, because detector is the mass spectrometer. That's why mass spectrometer is the detector, because the gas that comes after separation you see in the gas chromatography happening, and as it separates out, it immediately enters into mass spectrometer. When it enters into the mass spectrometer, it produces a mass spectrum. So what is mass spectrum? We'll discuss that today also. Which means each individual compound as it exits going into mass spectrometer producing a mass spectrum. So you're getting gas chromatogram, but a mass spectrum is also produced at the same time. So you can see the separation of the compounds, and for each separated peak, there is a mass spectrum for that compound as it passes out. So ideally, the way it works, it continuously takes mass spectrum. Continuously meaning there are few seconds delay, I suppose. I don't remember how many seconds delay. Let's say every couple of seconds it produces a mass spectrum. But you are mostly interested in the mass spectrum corresponding to the distinct peak, because that corresponds to one compound. So one compound as it comes out, let's say T1, goes into the mass spectrometer, produces a mass spectrum. So mass spectrum does something interesting, fancy thing, which is what we are discussing in mass spectrometry. So now we understand when we see GCMS, the word GCMS is used. Let me write it down here as you have seen there. GC dash or hyphen MS, basically meaning gas chromatography followed by mass spectrometry. Okay, so first part is your gas chromatography. Goal is to separate compounds in a mixture. Gas chromatography followed by mass spectrometry. Now, whenever you get an absorption signal, that is usually called spectrum. For example, IR spectrum, UV spectrum, NMR spectrum. But gas chromatography is not that. Okay, because here it's not a absorption spectroscopy. That's why they are using slightly different name. For the output from GC is called gas chromatogram. Output from mass spectrometry can be called as mass spectrum. That is good. So output from each one, here if I say, since it's a good idea for you to know that, gas chromatogram, that is the output, meaning the picture, and on each separated component in the gas chromatogram produces a mass spectrum. So mass spectrum tells you sometimes the actual identity of the compound. So you can separate at the same time find its true identity when these two techniques are combined or coupled together. Coupled would be more nicer term. So how this mass spectrometry works, I will tell you. It will not take all that time. We will be finishing on time. So mass spectrometry works like this. Here, if you take a look on this diagram, and on the top here it says, an organic molecule showing with an M is irradiated with high energy electron beam. Unlike electromagnetic radiation, light radiation we used in other spectroscopic techniques, IR or UV, here it is an electron beam, and 70 electron beam is very, very powerful, strong electron beam. It is so powerful, it can quickly knock out an electron from the molecule. As it knocks out, the very, very first instance, first millisecond or nanosecond, what happens is one electron is knocked off from the molecule, turning the molecule into a radical, because one electron is gone. Here it says plus one electron. Since the molecule is still intact, okay, but maybe it's weakened because electron is gone, and losing one negatively charged electron itself become positively charged. But it is also a radical because it has an odd electron. That's why it is called a radical cation or molecular ion, because it is the ion of the entire molecule. Okay, so it is a cation because it's positively charged ion. It is also a radical. That's why it is also called a radical cation. So both terms, molecular ion is a radical cation. Both terms are used. So that's first instance that is happening. And if we can identify its actual mass, by actual mass I actually do not mean mass in terms of gram kilogram. It is the mass number that you know of in that sense. Then you can find the atomic mass. Not atomic mass in this case, molecular mass. So molecular mass means molecular weight. That gives a huge amount of information. But that's not all. As this molecular ion, as I said, it forms only in the first millisecond or nanosecond, electron beam still is irradiating it. making this molecular ion to break down further. It breaks down into all possible fragments. Those fragments are then passed through an accelerating field of potential, and that moves the positively charged ions forward, not the negatively charged one, not the neutral radical, not neutral molecule, but only that is positively charged. Things that are not positively charged, they get pumped out. Here it says an arrow to pump, to vacuum pump. It goes out because that positively charged ions are deflected in the magnetic field. So there is a huge big magnet on the way at an angle. Here, let me show you another diagram. Both will indicate the same thing. So here is sample you put in. It is heated, forms gas, ionizing beam, electron beam irradiates, molecular ion forms as well as fragmentation occurs. Positively charged ions are moving forward, deflected inside this huge magnet. And these deflected ions are then analyzed based on their mass to charge ratio, m/z. Okay, and detector detects that, and that is what is a mass spectrum. Here is another diagram showing the same thing. As you can see, the sample goes in, electron beam breaks it down, magnet separates them, and they are separated by their mass to charge ratio. Detector detects it, producing a mass spectrum. So mass spectrum would look like, let me show you, here is one. Here is a mass spectrum, for example, of a molecule called hexane, 6-carbon alkane hexane. So what you see here, it shows intensity versus mass to charge ratio. That is the graph, and it gives you vertical lines. It only gives vertical lines. But because it is mass to charge ratio, that may correspond to mass. Reason for that, even though it is technically mass to charge ratio, it is mostly charge 1. As you would understand, a carbon with a positive charge is already quite unstable, high energetic entity. It is extremely unusual for a fragment to have 2 positive charges, right? If it is forms immediately, that is going to break down quickly enough. So vast majority, or in fact almost all of them, are single positive charge. So if it is single positive charge, then mass to charge ratio becomes mass, because charge is always 1. Single positive meaning 1. But technically, theoretically, we must say it is mass to charge ratio to be technically accurate. Otherwise, engineers or physicists are going to scold us. So we have to call it mass to charge ratio. But for all practical purposes, that is their masses. So you can guess the mass of the molecule, which is molecular mass or molecular weight. You can also get the masses of the fragments. So here on this diagram, on the right hand side, here it says m plus dot is the molecular ion peak. That is the largest molecular mass, because highest mass you can get is the mass of the whole molecule without losing any other atom. But you also get all other possible fragments. This fragmentation is occurring inside that chamber where this electron beam is still irradiating. Here is a sample. For example, if you imagine hexane molecule showing on the left hand side, hexane molecule, maybe I'll copy and paste on these applications so I can write on it better. So here, so what I'm showing is this. Here is the hexane molecule. initially after one electron being knocked off, this is the molecular ion peak. Here is your M plus dot. So you need to be writing it as M plus dot, and then it further breaks. Now, how many ways it can further break? It can break in all possible ways. For example, it can break along any carbon. It can break in along this carbon, along this carbon, along this carbon. Any carbon to carbon sigma bond can be broken because the radiation energy is very, very high. That is what is showing on the right hand side. It is showing molecular ion 71 plus the CH3 radical. Meaning molecular ion was 86, whole thing, this section's mass is going to be 86, but CH3 is actually that corresponds to 15, 1 carbon 12, 3 hydrogen 3, 12 plus 3 15. So molecular ion minus 15, meaning 86 minus 15 is going to be 1. That is another fragment. Likewise, if you 2 carbon cuts off, then you get a 4 carbon fragment. If 3 of them goes up, 3 carbon fragment. 4 of them goes up, 2 carbon fragment. So you are getting molecular masses of all other fragments, such as molecular ion 71, 57, 43, 29, all these things. But wait, that's not all. Even on each, which by the way, if I show you here, you have 71, 57, 43, 29. Those are the ethyl, propyl, butyl different cations. But other than that, it is also possible that from any fragment, 1 hydrogen can be lost. 2 hydrogens can be lost. 3 hydrogens can be lost. So basically, it's not only carbon-carbon single bonds, all carbon to hydrogen bonds can break as well. Just imagine if you have a carbon like this and you have hydrogens, then all hydrogens can also break off here, 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 producing fragments which is 1 unit less or 2 number less or 3 number less. So mass number can be 1, 2, 3 unit less than each individual fragments. And that is exactly what you are seeing. For example, if you look at this one, the one that is 57, you also see something 56, you see 55, you see 54, because 1, 2, 3, etc. number of hydrogens can be stripped off as well. That is the fragments you are getting. And you see next jump is again 43, because that means an additional carbon is now gone. So that is the mass spectrum, and you see the fragments. Now, here is a term. This term does not have a huge, big meaning, but has some meaning, is the base peak. What base peak means is among these fragments, the fragment that has the highest intensity corresponds to highest abundance. Highest abundance meaning highest concentration. Who is going to have highest concentration? The one that is most stable, right? So the most stable fragment will produce the base peak. Its intensity is going to be the highest, top. You see this one is 100% intensity for 57. That's it. There is no other meaning beyond that. So base peak is the one tallest peak, highest intensity, that is from the most stable fragment. That's one other understanding. Now, while all this fragmentation analysis should be done, can be done, keeping in mind what is most valuable to us is this last one, molecular ion peak. Why? Because that corresponds to molecular mass. This corresponds to molecular mass. Molecular mass. Molecular mass is the same thing as molecular weight. So other techniques that you have learned, none of them give you molecular weight. But this one does. That helps to decide a lot of things. That's one aspect. Another aspect of this, I'll tell you a number of aspects. Listen carefully, it's actually interesting. Another aspect is each molecule is going to produce a particular mass spectrum. For hexane, it is going to be just like this. That is going to be its fragmentation pattern. So the mass spectrum that is generated from the molecule, which is coming, as you know, from originally from GC, finally from your mass spectrometer, coming as a mass spectrum, that particular mass spectrum is for that particular compound. If you think of being compiled or coupled with GC, just imagine, as you saw in GC, one of the peaks being hexane. So one of the peaks going into the GC producing a mass spectrum, and you can see its mass spectrum. You can analyze them, and you will do that and have fun. But there is another interesting thing. If the compound is very big, complicated, various functional groups, and you cannot possibly solve it, nowadays this mass spectrometer comes with some additional software. As you know, science actually is propelled by economics quite a bit. Economics actually helps, business actually helps science. Science helps business, business helps science. Science is supposed to help improve our lives, which is what it does in some countries, right? Here also it does to some extent. Like we saw, this COVID vaccine is a big breakthrough. Now, going back to this, the mass spectrometer may come with an inbuilt software that has a library of mass spectrum. A library, meaning your library, like your city college library, has thousands of books. This mass spectrometer can store thousands or even million different mass spectra in its memory. If it does, then as soon as the mass spectrum is generated coming out of mass spectrometer, it can also quickly, as it is done, it is stored, of course, in its memory. You are going to get a mass spectrum or GC followed by mass spectrum. And that, as I said, from the stored library, you can search for the identity of the mass spectrum that you have gotten from an unknown compound without having to analyze in a difficult way, peak for peak. You can do a search and it will search through its library and see if it finds a match. And it will, of course, find a match if it has a library. And of course, library, how many it has depends on how much money you pay, right? It has smaller library, bigger library, depending on the price. So in a bigger library, let's say you have a bigger library, so that can, your spectrum that you are getting, it can search it, compare and search with the inbuilt library of spectra and tell you that your compound or your spectrum is for the possible molecule is this. It will actually give you a list of names of compounds, what your spectrum might be for. Funny thing though, machine is, after all, machine, they are not humans, right? Machine will give you like this. It will 99% probability your molecule is hexane. And it will say 96% probability it is this, or 80% probability it is this. So obviously the one that is of highest probability, that is almost always is the correct compound. Yeah? That's just additional thing to know, that you can search your spectrum, search and compare with inbuilt library of spectra that is in the machine. So this is what the mass spectra does. So here I will show you a smaller molecule like one carbon. As you see, 16 is the total mass. Molecular ion peak is 16, but you also get other fragments. 3 carbon molecular mass 44, but you get other fragments, hydrogens up, or even entire carbon up. Okay, so that is the mass spectrum. Now, few additional things can be found from this. Here in the text, you might also see here is a molecule, a branched molecule 2-methylpentane, and you might see that is what is it called? Isopropyl carbocation is 2-degree carbocation being more stable. That turns out to be the base peak. The topic that we just mentioned, most stable carbocation fragments gives the base peak or the most intense peak. So likewise, you get very many different peaks. So far I am telling you that you can get the molecular mass and you can search against library, etc., etc. But wait, there are a few other very interesting things you can also find from a mass spectrum. Those are these. Now, if you were to imagine natural abundance of different elements, hydrogen 1 being 100%, we discussed in NMR, carbon 12 is 98.9, we discussed that, and carbon 13, 1%. But here, three elements are very interesting. Halogens. Chlorine that you write as 35, that's actually 75.5%. There is an isotope of chlorine that is chlorine 37, that is 24.5%. If you round up about 25%. So 75% chlorine, naturally occurring chlorine, 75% is chlorine 35, 25% is 37. 3:1 ratio. That is going to reflect on the mass spectrum. So if you have a chlorine, you are going to get 2 peaks as your molecular ion peak, because molecule may be made up of chlorine 35 or it may be made up of chlorine 37. So both are molecular ion peaks. So in a sense, you will get 2 molecular ion peaks, 2 units apart, 35 and 37, 2 units apart, and 3:1 intensity ratio, because 3 times 35 is 3 times the intensity of 37, 25 versus 75. That is going to be chlorine, and I'll show you that with examples pretty soon. Let me also indicate at the same time is bromine. On the other hand, bromine atomic weight is 79, atomic mass. That is 50%, 50.5 to be exact. And bromine 81 is other 50%, 49.5 to be exact. So they are almost equal, 2 isotopes, which means your peak intensity will be 1:1 ratio, 2 units apart again, 79 and 81, 2 units apart. So what we are getting is this. If in a molecule you have a bromine, here you see on this spectrum, the top one is the one with the bromine. You see molecular ion peak consists of 2 peaks, 2 units apart, and they are equal height, because bromine 79 and 81, they are 50-50. And that is the feature you see. Now, using your logic, for an unknown molecule, in your mass spectrum, if you see that you have molecular ion peak consists of 2 peaks, 2 units apart, equal height, then you know your molecule has a bromine. That's a huge useful information. And bromine being so heavy, if you subtract 79, you are going to get the rest of the fragment. Likewise, look at the next one underneath, the chlorine. Here is a 2-chloropropane molecule. When you have a chlorine, because their natural abundance 75 to 25%, you see your molecular ion peak consists of 2 peaks, 2 units apart, 3:1 ratio. 78 is 3 times taller than the 180. Okay. Inspect carefully. These two peaks are 3:1 ratio when you have a chlorine. So these two piece of information is quite valuable when you are analyzing an unknown molecule. Okay, so if the molecular ion peak consists of two peaks, two unit apart, unit meaning mass to charge ratio, basically mass, and 3:1 ratio their peak height, then your molecule has a chlorine. If they're two unit apart but equal height, then your molecule has a bromine. So you are getting two additional pieces of information in addition to the molecular mass, molecular weight of the molecule. You are also getting information about presence of chlorine or presence of bromine. You also know the most stable fragment, right? That is the base peak. But wait, there is another interesting thing. Whether you have a chlorine or bromine, or you have no chlorine, no bromine, there is one interesting thing. In all cases, the molecular ion peak is an even number, even versus odd. Let's say the top one, 122, 124. Next one, 78, 80, even number. Even if you go for the other molecule, the hexane we discussed, that is 72, even number. So whether you have a chlorine or bromine or none, molecular ion peak is always an even number, with one exception. If you have a nitrogen on the other hand, then the molecular ion peak becomes an odd number. Well, let me find an example with the nitrogen. It's probably this one. No, not that. Here is ethylamine. Here is another one, pyridine. Here you see the molecular ion peak is 79. That's an odd number. So whereas all molecular ion peaks are even number, if you have a nitrogen, pyridine has a nitrogen, you know, then it becomes an odd number. So that is giving you an additional information that if your molecular ion peak is an odd number, then you know there is a nitrogen. That's useful. Here is a molecule with a chlorine, like chlorobenzene. You see the molecular ion peak 2 unit apart, 3:1 ratio, because chlorine should have 3:1 ratio. Here is a bromine containing bromobenzene. You see 2 unit apart, almost equal height. Because actually not exactly 50-50, but 49.5 and 50.5, as you know. So that is giving you an additional piece of information. So now you can see how many things we have learned so far from a mass spectrum. What are the useful informations you are getting? Useful information. You are getting number one, you are getting molecular mass. That is the molecular ion peak on the extreme right. Molecular mass, right? That corresponds to the molecular ion peak. Number two, you can get most stable fragment. That's not as important a thing. Very important is presence of chlorine. Because if you have a chlorine to chlorine, then your molecular ion peak with molecular ion plus 2, their ratio is going to be 3:1, 3:1 intensity ratio. Likewise, if you have a bromine, let me write like presence of bromine. In that case, molecular ion to molecular ion plus 2, that is going to be 1:1 ratio. Finally, we are learning another thing, which is if you have a nitrogen, odd mass number or odd mass number, or I should say molecular mass, odd m plus dot, right? Molecular mass number corresponds to presence of nitrogen. Presence of nitrogen. So you're getting quite a number of things. Okay. Now, so these are the useful information, and that is what you are going to be learning. Our GC+MS machine was used to be in our Barshak building, and it was giving problem all the time. We did not have a good expert to maintain it correctly. So this summer the machine was moved to what is it called? The other science building, and I am not sure whether TAs are going to take you there. Probably not, but we will have access, and we will get a mass spectrum made, printed, and brought in. That may be happening. Konga will give you more update on that. But I heard from Professor Bisco that it was taken away. Now, in addition to all this that I just said, there is one extra thing I want to point out. If a molecule has a hydroxyl group, sometimes a molecule of water is lost. Hydroxyl and hydrogen together makes the water, and sometimes 18 unit can be lost from the molecular ion peak, and sometimes molecular ion peak may be not even observed. You will be getting molecular ion peak minus water. That can happen in few cases. Where is one of those? I want to show you. Anyhow, you can check it maybe in one of those. 18 unit may be lost, giving you a slightly convoluted mass spectrum like this one. When you have a hydroxyl group, molecule of water is lost. Here, this is one. Sometimes a molecule of alcohol can be lost also. Here is it is showing M plus dot minus water. Here you see my cursor. So that's one thing. Lastly, there is one interesting thing called McLafferty rearrangement. This happens with carbonyl containing molecules, like in a ketone, most commonly in a ketone, can be in an aldehyde also. As you can see, this ketone molecule, from its gamma carbon, alpha, beta, gamma, the gamma means alpha is the next one, then beta, then gamma. That gamma carbon's hydrogen rearranges onto oxygen, and then it eliminates a molecule of ethylene, CH2CH2. Meaning, your molecular ion peak sometimes can be lost, and CH2CH2, which is 28 unit can be subtracted. Or you may get a molecular ion peak, but you will also see the next fragment is not really matching very well. No, you will get a molecular ion peak. It's not molecular ion will be lost. Molecular ion peak will be there. But you will see your next fragment is molecular ion peak minus 28. That 28 is coming from this CH2CH2 ethylene molecule formed from this McLafferty rearrangement. Okay. All right, guys. So this is all the discussion about mass spectrometry, and it is combined with GSGC, as I mentioned at the beginning. Together makes a powerful method. In a lecture, I usually class I post it in what is it called, in Blackboard. I will be happy to post it on Blackboard. Those who wish to review from this, but also make sure you wrote down some important features I mentioned here, and these are also being recorded, so you have it. All right, guys, any questions? That's all today. All right, guys, Anastasia, Yuan, MD. Well, it is going to be regular class time, 50-minute test, which means there is going to be some very short questions, and there may well be one or two multiple choice. Basically, it is something that you can finish in 50 minutes. So generally, it will range between 10 and 15 questions. Roughly 15 would be a good number to indicate. Okay, no more than 15. All right. Good, good. Good night, Anastasia. Good night, everyone. Welcome. We are. Bye bye. So I will stop recording.